this session. So I will say it again. I'm Ingrid Van Keilegom, and I'm the chair of this session. So I will start with a small presentation, which is going to introduce the topic of dependent censoring. And then after my presentation, Mirte Daan will talk about quantile regression with dependent censoring. Okay, I suppose you can see my slides. Okay, then I will get started. So I will briefly introduce the topic of dependent censoring, and then I will talk about a proposal that has been made in a paper together with Claudia Czado in Biometrika. And then at the end, I will talk about a number of extensions. And one of these extensions will be the paper by Mirte Daan, which she will talk about after me. So we are in the context of survival analysis, and we suppose that we have a survival time T and a censoring time C. And we have random right censoring. And so that means that instead of observing the T that we would like to observe, we observe in general the smallest of T and C, which is denoted by Y. And we also know what we observe, and that's given by delta, and delta is equal 1 if we observe a T, and it's equal to 0 if we observe a C. Okay, so that's the context of random right censoring. And so what we would like to do is to estimate, let's say, the distribution of T or the survival function of T. But because of random right censoring, this is not so straightforward. So usually in the literature on survival analysis, people make the assumption that T and C are independent random variables. Why do they make this assumption? Because in practice, or usually you only observe the T or the C for a given individual. And so you cannot identify the link in a non-parametric way, at least you cannot identify the link between T and C. And so since you cannot identify that link, you have to make an assumption on that relation between T and C, and the independence assumption is the most natural assumption. And if you make that assumption, then you can estimate your distribution of T. So this goes back to very old papers like the seminal paper of Buchtsiatis in 75. Yeah? So most of the literature on survival analysis assumes independence between T and C. Now, you cannot test that in a non-parametric way. Again, for the same reason, because you only observe a T or a C, and usually not both. And so you don't know what the relation is between these two. Yeah? But you can sometimes tell from the context whether an independence assumption makes sense or not. And a very common situation in which independence between T and C makes sense is when you have censoring at the end of the study, which is called administrative censoring. So in that case, you might say that the fact that you reach the end of the study has nothing to do with your survival time, and so you have independent censoring. Yeah? There are also many other cases in which independent censoring does make sense, but there are also situations in which independence between T and C is doubtful. And here are a few examples. So let's look at the first example, again, coming from medicine. You might have patients who decide to withdraw from a study for reasons that are related to their survival time. So, for instance, a patient who is having severe side effects of a treatment or who is very ill and might be close to dying, that patient might drop out from the study, and then it's clear that it's related to his health, and so indirectly also related to the survival time. Yeah? Or you might have the opposite situation, so a patient who is feeling very healthy and decides to stop the treatment. Then again, the fact of stopping and so being censored is related to his health and so to the survival time. In the first case, it might be a positive relation between T and C. In the second case, it's a negative relation. Okay, here you see a few other examples coming from economics or from transplant studies, where again, you might argue that censoring happens for reasons that are related to the survival time, and that then creates dependent censoring. Okay, here you see what happens if you would assume independence between T and C, when in reality they are correlated. So it's a small artificial data set of size 200, and I generated T's and C's from a bivariate log normal distribution with mean 0, variance 1, and a certain correlation rho. And what I will show on the next pictures is the true survival function, which is a standard log normal. And I will compare it with the estimator, the Kaplan-Meier estimator that you get from these data. Now, the Kaplan-Meier estimator is the non-parametric maximum likelihood estimator that assumes independence between T and C. And so we expect that this estimator is going to be biased if in reality this correlation rho is not equal to 0. Yeah? And indeed, this is what you see. So in the figure in the top left corner, you see the case where rho is 0. So in that case, we have independent censoring, and indeed, the true survival function, which is the smooth curve, is close to the Kaplan-Meier estimator, which is the step function. Yeah? But then when you look at the other three pictures, this is for rho equal 0.3, 0.6, and 0.9. So you see that Kaplan-Meier estimator gets further and further away from the true survival function. And so indeed there is a bias issue, and the bias is always a positive bias. So the Kaplan-Meier estimator is overestimating the true survival function. If we now go to negative correlations, then we see a similar situation, but the Kaplan-Meier estimator is now underestimating the true survival function. So in any case, I hope that with these pictures, you are convinced that we should take dependent censoring into account to avoid bias estimation. Okay, so now what are possible approaches to handle dependent censoring? Well, there are several approaches, but I will focus here on an approach based on copulas. Now, very quickly, what is a copula? So it's a bivariate distribution that is defined on the units square and that has uniform margins. That's the definition. And why are copulas useful? Well, that's thanks to Sklar's theorem, which says that if you have two continuous distributions, let's say F and G, then there is always a unique copula such that the bivariate distribution of T and C can be written as that copula evaluated in the marginals. So in a sense, a copula is a bivariate distribution, but you take out the margins. So it allows you to model the dependence between two random variables without having to worry about margins because the margins are extracted from that copula. And so in a sense, thanks to this Sklar's theorem, you kind of separate the margins from the dependent structure between two random variables. And so the copula is only looking at the dependent structure without taking these margins into account. And so that's a very nice result, because you can then model the margins and this copula separately. And so in particular, if you have independent random variables, then of course the bivariate distribution is a product of the margins. So it means that the copula is simply the product of the two arguments. So that's a very special case, but you might have other copulas. For instance, there are parametric copula families, like Archimedean copulas or elliptical copulas. And then special cases in these families are, for instance, the Frank, the Clayton, the Gumbel, the Gaussian, etc. And here you see two examples, the Gumbel and the Gaussian, which depend usually on one parameter, let's say theta, and then for a particular choice of that theta parameter, you get back the independence copula. Yeah, so it allows you to model relationships between random variables, which includes as a special case the independence case. So this looks very appropriate in our context, because if we model this relation between the survival and the censoring time with a copula, then we might be able to capture not only independent censoring, but also dependent censoring. And so indeed, this idea of using copulas to model dependent censoring, it has been used already for quite some years. It started in '95 with a paper by Zheng and Klein. And then later, their proposal has been worked out or extended in other contexts. Now, all these papers are actually very nice. They really allow for dependent censoring, but they have one drawback in common, and that's the fact that this copula always has to be fully known. So, for instance, it has to be a Frank copula with a known parameter. So it means that you have to know how strong the association between T and C is. And in practice, usually you don't know that. You might have an idea whether it's positive or negative or zero, but the precise value you usually don't know. And so all these papers, they are useful for sensitivity analysis, because you can see how much your estimator changes when you change the value of that parameter. So for that, they are useful, but they are not that useful to do point estimation. So this is where we wanted to make a contribution. And so now I come to, to our proposal. So what is our proposal? We would like to have a model in which we can estimate this copula as long as it is belonging to a certain parametric family. So in the first paper that I'm going to present now, we did this in a very simple situation, in the sense that we assumed that the distribution of T is fully parametric, the distribution of C is also fully parametric, and the copula is again fully parametric. And in this setup, there are no covariates. So yeah, it's the most simple situation that you can think of. But still, the question of whether we can identify the association parameter theta was not easy. So I will explain now how we did that, and then at the end, I will talk about extensions of this model. So as you see, we have to pay a price compared to the previous papers, because if you go back, for instance, to Zheng and Klein, they assumed non-parametric margins with a known copula. And so we can, work with an unknown but parametric copula. So in that sense, we are more flexible. but the price to pay is that our margins are now parametric. And so later on in the extensions, we will see how this can be extended to semi-parametric models. Okay, and so the question we want to ask now is whether this is identified. Now, at first sight, you might say, well, everything is parametric, so it should be identified. But this is not necessarily the case because in the context of random right censoring, we don't observe the T and the C. If they would be observed, then indeed everything would be easy. But instead of observing T and C, we observe the minimum and the censoring indicator. And so the question is whether with the information about the minimum and the censoring indicator, can we still identify these three parameters? So here is indeed our definition of identifiability. So we start from the density of what we observe, so the y and the deltas. And if we would have two equal densities under these parametric assumptions, and these densities will depend on all parameters, which I denote by alpha. So if these densities would be equal for an alpha 1 and an alpha 2, does that then imply that the two sets of parameters have to be the same? Yeah, if that's the case, then the model is indeed identified. And so what we did is we developed two sets of conditions under which we have indeed identifiability. And so the first condition, the C1, says that the parameters of the law of T and the parameters of the law of C, they can be identified just by looking at the limit of the density of T and the density of C for two sets of parameters when the time either goes to 0 or to infinity. And if that limit is equal 1, then it should imply that the parameters are the same. Yeah, that's the condition that we impose on our parametric families for T and C. We check that condition for specific parametric families like the Weibull, the exponential, the log normal, the log logistic, and each time it turned out to be valid. Yeah, so this is not that a severe condition. And then the second condition, the C2, this is regarding the so-called H functions. And the H functions in the context of copulas, they are the partial derivatives of the copula with respect to the first and the second argument. Yeah. And so we also have to assume that these H functions, when t goes to 0 or when t goes to infinity, that their limit is also 0 when you evaluate them in ut and vt. And ut and vt are the marginal distributions of t and c in the point t. So this is a bit more abstract, and it turns out that this is not always the case. So for some choices of copulas or certain choices of marginal distributions, it could be that these limits are not 0. Yeah. In any case, here is then our final identifiability result. So we show that the model is indeed identified if C1 and C2 hold. And as I said, so when are now C1 and C2 satisfied? Well, C1 is satisfied for log normal, log student T, Weibull, log logistic. So that's fine. For condition C2, it's a bit harder. It's not always satisfied. So here you see three examples. If you take the Frank copula, it's always satisfied. And for the Gumbel and the Gaussian, there are two sufficient conditions that guarantee this condition C2. Now, these sufficient conditions, we looked at them for particular cases. So if you take, for instance, two log normal distributions or two Weibull distributions for T and C, then you can show that this sufficient condition for the Gumbel is satisfied. And for the Gaussian, it's a bit more complicated because the formula of the Gaussian copula is, it's more complicated. So we could not show it explicitly, but we showed numerically that it is also valid for many marginal distributions. Okay, and then finally, the estimation. This is quite simple because it's a fully parametric model. So once you know that it's identified, you can write down the likelihood and then maximize that likelihood. Now, the formula of the likelihood is a bit more messy than what you usually have with right censoring because, because of this dependent censoring. But in any case, we have an explicit formula which depends on all the parameters. And so we can maximize this log likelihood over these parameters, and that gives us our maximum likelihood estimator. Okay, I think in the interest of time, I will skip the simulations. So we do have simulations in the paper that show that everything works well. So the bias is quite small. The variance gets smaller with the sample size, etc. So let me maybe still talk about a few extensions for the remaining 5 minutes. Well, before I get to the extensions, here is the reference of the paper. So it got published in Biometrika last year. And you also see the QR code in case you are interested. And we also have a package, depth censoring, which is since a few days on the CRAN. And so you also can download it by scanning this QR code. Okay, so let's go to a few extensions. So as I said, this paper that I presented is the most simple context you can think of. It's fully parametric and there are no covariates. So the first thing we did was we tried to add covariates while still keeping a fully parametric model. And this was published actually before the paper that I presented. It was published in 22 already, but it was actually written after this first paper. So that was the first extension. And then the second extension we worked on was a semi-parametric model. And we made it semi-parametric by assuming a semi-parametric Cox model for T. And so we have covariates, of course, and then in addition, we have a semi-parametric Cox model. The copula was still fully parametric, and also the censoring time still followed a fully parametric model. So this was, I think, a nice extension because it allows you to work with the very common semi-parametric Cox model while still taking dependent censoring into account. So this was also published in the meantime quite recently, and then we also have a package for this paper. And then here are a few more recent extensions. So one is where T and C both follow a semi-parametric model. One is with confounding factors. One is about dependent censoring with Cure models. And the paper that Mirte will talk about in a minute is this one, which I put in a frame. So it's on quantile regression under dependent censoring. And then a final paper is on a boosting approach to deal with dependent censoring. Okay, this is my last slide. So it's on what is on the agenda or what are we currently working on together with mostly PhD students. So we are working on a goodness of fit test, because that's of course important, because you always have to make some assumptions. So it would be good to have a way to check these assumptions. We are also working with a PhD student on partial identification results. So that means that you are not trying to fully identify your distribution of T, but you want to have boundaries between which the distribution will lie. We also try to have a non-parametric model for T, but in that case, you have to have a parametric C and a parametric copula. It will probably not be possible to to have semi-parametric models for C and the copula, for instance. And then finally, the two last points, I put them in red because, I think they are maybe also very useful. So the fact of making these dependent censoring models more broadly known to more applied people, that's also something that we have on our agenda. And so, for instance, we had a very recent collaboration with Merck, in which they realized that they have lots of dependent censoring in their data. And so they, we are discussing now how they can deal with that problem. And then finally, making the work known through talks like this talk or short courses. That's also something we have on our agenda regarding our work on dependent censoring. Okay, I think I will stop here in the interest of time. I don't know whether there are questions or should we go immediately to the second talk? I think we can go to your talk, Mirte.
Thank you, Ingrid. I will share my slides. Okay. So hello, everyone. I am Mirte Daan. I'm a PhD student supervised by Ingrid Van Keilegom and Annelien Brasselt. And as was just said, I will introduce the extension of the previous work to the quantile regression setting, where there is dependent censoring with an unknown destination parameter. I will start by giving a motivating real data example, and then I will introduce the necessary theoretical material and present a few simulation results to in the end get back to our real data example that we will then analyze using our methodology. So the data that we will consider has been analyzed before in the context of dependent censoring, and it's about liver transplants. So more specifically, it originated in a study on the mortality of people on a waiting list for liver transplants in the United Kingdom. And the data set consists of about 280 patients of a specific liver disease that were registered for receiving such a transplant. But then because of a shortage of livers available for transplant, some of them die while waiting for a liver. And so for them, we have a survival time, but unfortunately, many of them also receive a transplant, which is considered censoring here. And then for all the patients, we also have some information available. So for instance, it contains the UK end-stage liver disease score, which is an indicator of how severe the disease is. So the higher the score, the more ill you are. Now, as you can see, there is quite some heavy censoring, and there's also indications that this censoring is actually dependent. You can see this by looking at the plot that already indicates positive dependence between the time to death and the time to transplant. And also, it would make sense that patients that are more ill are both more likely to die soon and to receive a liver transplant. As I said, it has been analyzed before. It has been done using a weighted Cox proportional hazards model. And in a more recent paper also two other models were studied. One of them was a copula model as one that we will be using, but their association was still fixed. Common results were that only the Euclid score turned out to be significant, and moreover, the dependence was indeed positive as we expect, or as they expected. For instance, the correlation was estimated to be about 0.7. So that's a really strong correlation that should indeed be taken into account when analyzing this data. So it cannot just be ignored. Now, what is different in our analysis? We will also work with this dependent censoring, but with a flexible association parameter. And moreover, we will take the quantile approach. I will motivate this in a few slides, but one reason is already that we can do inference for the entire distribution of the survival time and not only its mean. So now I will get back to the more theoretical part. Our setting is the same as in the previous talk. We have the same notation as before, except that our survival and censoring time are logarithmic, so they can also take on negative values. And we will work in a regression setting, which means that we'll also observe some extra information in the covariate X. Now, I don't think I need to motivate the copula models any further. So the theoretical motivation has already been given in the talk that Ingrid just gave. Where the crucial part was this non-parametric non-identifiability by Czado. And then for the practical side, she also already gave quite some examples. And we also have this liver transplant example where indeed there is, we cannot just assume independent censoring. Now, as was also pointed out, the strength of the association parameter is in practice typically not known. And so therefore we will use this recent paper by Czado and Van Keilegom, where we can identify it based on the data. Now, this is some more notation that is the same as before. So we have 3 families of parametric distributions, one for the copula with the parameter theta, and then 2 marginal distributions. And as I said, we work in a regression case. So we will include the information of the covariate X in the margins. In our work, we assume that the copula parameter theta is covariate independent, but actually you can also relax this assumption and extend this to depend on X's. Now, as promised, I would give a little bit more motivation on why we take the quantile approach. So, well, just to be on the same page, I put the definition of a quantile here, but I guess you all know it's the inverse of the distribution function. And quantiles have, in recent decades, become quite popular because they enjoy some nice properties over the traditional mean regression. So just to name a few, it's more robust against outliers. And as I said, you can do inference on the entire distribution. Now, specifically in the context of survival analysis, it also has a, well, it has been argued that it has a more natural interpretation than, for instance, the proportional hazards or accelerated failure times. So quantile regression has been studied in survival analysis quite a lot already. And of course, survival often comes with censoring. So that's why there is actually already quite some literature available on censored quantile regression. And I put just a short selection on the slide here. As you can see, there is 2 categories. So first we have the one assuming that the censoring is independent, and that originated actually already 40 years ago in a very easy setting, and then gradually more complicated and also more relevant cases for practical use have been studied. Let me just point out here that there is also some papers that use an asymmetric Laplace distribution to actually get the quantile orientation in their work. So one of them was a paper by Botai and Zhang, but their estimator turned out to be inconsistent. And then in a very recent, still to be published paper, this asymmetric Laplace distribution was extended to an enriched asymmetric Laplace to obtain sufficient flexibility. And this will actually be important for our work because we will also work with this enriched asymmetric Laplace distribution. Now, on the other hand, there is a category of the dependent censoring papers in quantile regression. And here I actually didn't make a selection, but to the best of our knowledge, there's only 2 papers available. One of them assumes that the association parameter is fixed. And the other one is pretty close to our context. They also work with copula models, as we will do. They also have an unknown association, but with the important difference that they only perform partial identification, so set identification of the parameters, rather than the point identification that we will consider. So now that I've positioned our work relative to the existing literature, let's dive into the model and its main components. So let's say we're interested in quantile of some level lambda between 0 and 1 for the survival time, and we assume that it's linear. Now, of course, we want to take this dependent censoring into account, so this wouldn't really make sense to just start from only a marginal model, but rather we will start from a bivariate model, in this case a parametric copula model, and then from this model afterwards we will derive the quantiles for the survival. Now, for the margins, we just take a simple parametric model for C. So you can, for instance, think of a normal distribution there. But then on the other hand, we're mainly interested in the survival time T. So there we will make a very specific construction for the distribution of the error term that I will get back to in minutes. Now, let me just already point out that the model is actually fully parametric, even though the number of parameters will grow large. But so in particular for the estimation, this implies that we can, as in the previous talk, just apply maximum limits. Now, one last thing. So we should actually check that the model we intuitively would have wanted to start from, so the linear model, is compatible with a bivariate model. And this is indeed the case whenever a lambda quantile of this error term equals 0. So this is something we will have to take care of in constructing our term for T. So for this error term, we will start from an asymmetric Laplace distribution because, as I already hinted at, it is closely linked to quantiles. I won't go into details here, but quantiles are actually equivalent to performing maximum likelihood in an asymmetric Laplace framework. So that provides an heuristic explanation for why we would start from an asymmetric Laplace distribution. Density is given here. You can show that indeed it satisfies the vanishing quantile property, but on the other hand, it's not really flexible yet, whereas actually we would want to be able to approximate any relevant density function. And in order to guarantee this, we will include a linear combination of Laguerre orthogonal polynomials on both sides of the real axis. Now, it's important that these polynomials are orthogonal with respect to this exponential weight to ensure that this vanishing quantile property is preserved. And on the other hand, if we let the maximal decrease tilde and m of these polynomials grow larger, then it can be shown that you can actually approximate any relevant density function in the Hellinger sense. So this means that with this enriched asymmetric Laplace distribution, if we take the number of parameters sufficiently large, then we attain any flexibility as we want. And yet it's still a parametric model. So we still hope that it's identifiable. And indeed, we have shown that it is identifiable. Now, as already pointed out, the simple parametric model, well, it may seem straightforward that it would be identifiable, but then of course the model is on the level of the latent survival and censoring time, whereas our observations are on the level of y and delta. So it's actually not at all straightforward to show this identifiability, but you can indeed show under a list of additional assumptions that whenever two sets of parameters yield the same likelihood contributions, then they must indeed be equal. Now, what are actually the parameters to be identified? So we have a copula parameter. Now we have two parameter vectors for the marginal distributions that in turn also contain vector elements. Now, let me just point out here that this parameter lambda, that is the level, the quantile level to which the linear quantile corresponds, is actually in some cases also part of the parameter vector to be estimated. So this is fairly non-standard, I'd say, in quantile regression, which we have a motivation for this that I will leave now. So it basically all comes down to this shift approach. So if you have any distribution, for instance, the enriched asymmetric Laplace, but also any other distribution for which the lambda quantile equals 0, then you can show that if your survival is specified in this location shift way, that any p quantile will be given by the linear lambda quantile plus some shift. And this shift is a variance term times the p quantile of this distribution. And so now you can see that if the sigma is linear, then by rearranging, all these quantile curves will be linear. Whereas on the other hand, if sigma is nonlinear, then there will only be precisely one linear quantile curve corresponding to this level lambda. So to give you a better idea of how this is linked to the identifiability problem, I just included a few plots here. So first, within the linear case, we can consider the constant case, which of course comes down to homoscedasticity. And then by rearranging the terms, you can see that any quantile curve has actually the same regression coefficient, but different quantile levels yield different intercepts. So this means that if you don't fix this parameter lambda, then you will never be able to identify this intercept that varies over the quantile. Then similarly for a linear non-constant variance, so in that case, if the constant part of your variance is 0, then the intercept will be identifiable because it's always the same, but on the other hand, the regression slope is not. And so in the general linear case, you can see that both the intercept and the slope will not be identifiable unless fixed lambda. So takeaway for this part, if you have a linear variance, it's important to fix your lambda in order to be able to identify the regression coefficient beta. On the other hand, as I said, in the nonlinear sigma case, there will only be one linear quantile curve, and so your model will be able to identify this specific level based on the data, and there's no need to specify it in advance. And actually, it's also better not to specify it because, of course, the probability of correctly specifying it is very small. So in that case, it's important to include lambda just as a parameter that also has to be estimated from the data. This shift approach, moreover, comes with some examples. So as I said, it has some the advantage that if you should not specify it, then you can also not misspecify it. And it also has some computational advantages. So the maximum likelihood estimation, that is actually a pretty heavy procedure here, has to be performed only once, and then all the other quantiles can just be obtained using the shift approach with some basic computations. And it also rules out the possibility of crossing quantiles. So after this important intermezzo on the parameter status of lambda, let us get back to the identifiability. So now we will assume that lambda is present in the parameter vector only in those cases which can be identified, of course. As I indicated, the proof is rather involved or at least lengthy. So I won't bore you with the details here, but let me just point out that we used an adaptation of the proof of the work that was just presented. So as you may remember from the last talk, we had these two conditions that had to be satisfied in order for the model to be identifiable. And one of them was this asymptotic identifiability of the margins. So knowing only the behavior at the endpoints of the support, we should be able to identify the margins. But in our case, or enriched asymmetrically plus, so the distribution for T is actually well, too flexible in a sense. So only knowing the behavior at infinity is not sufficient to identify it, and therefore we had to create an ad hoc modification of the proof. I will now say just a few words about the asymptotics. So under some extra regularity conditions, you can show that our estimator is consistent and asymptotically normal. This is on the level of the parameters, but actually using the delta method and using one mild extra assumption, you can also transfer this asymptotic normality to that of the quantile estimates. I will not go into the details of the proof here, but let me just point out that because of this asymmetric Laplace distribution, our likelihood is actually non-smooth. So you cannot just apply the standard asymptotics methodology as in white, for instance, but we worked with the extensions in Papes and Pollard. And then you can indeed show these results. So now I will move on to the simulation results. We did quite an extensive simulation study, actually, but I highlighted only a few results here. So let us consider a very simple case in which we have two log normal margins and about half of the observations censored. We considered both a heteroscedastic and a homoscedastic case. So remember, with heteroscedastic, we had this parameter lambda to be identified. Homoscedastic case, it was fixed. But now for this presentation, I will focus only on the heteroscedastic case. So first of all, this is just the basis scenario. I selected some values for the covariate X-tilde, and then some quantile levels, which are just the 3 quartiles here. And as you can see, the estimates get pretty close to the true quantiles. So that's the confirmation that the model with the variable lambda indeed works. Now, you might be wondering, well, in some cases, we don't really know whether there is dependence or not. So would it be harmful to apply our model to a data set that is actually generated under an independence assumption? The answer is no. As you can see, the estimates are actually really good. And also on the level of the parameters, which are not shown on the slide here, but the estimate for Kendall's tau is almost equal to 0. So even if you apply our methodology for dependent censoring to an independent censoring data set, then the model will really capture this independence. So it's not harmful to apply it. Now, of course, more interesting is to see what happens when there is actually dependence in the data. And so we considered 3 different model fitting procedures, but all of them were applied to a data set that was generated under dependent censoring. So first of all, what is unfortunately often done in practice is just to ignore the dependence and to naively apply the independence estimator. And as you can see, then the relative bias here can get pretty large. On the other hand, if you would apply dependent censoring model with a correctly specified copula family, so for instance, the data are generated with a Frank copula, and you also use a Frank copula for the model fitting, then the relative bias is the smallest possible. But then even in case you misspecify the copula, so for instance, you use a Gumbel copula for the fitting instead of the Frank copula, then still the bias is lower than in the case of the independence one. So in other words, in case where there is dependency in the censoring, applying our methodology is performance improving, even if you would misspecify the copula. And then all of this also holds for the homoscedastic case. So now finally, as promised, let us get back to the real data application. So we work on the logarithmic scale now for the margins. And well, since only this Euclid score turned out to be significant, we also included only that one in our analysis. We fitted our model with the EAL distribution to enrich the symmetric plus for the survival, and a simple normal model for the censoring. And if you look at the log plot on the right, you can see that the variance seems pretty constant. So we fitted several homoscedastic models. And then we selected the best one using the AIC criterion. So we worked in 2 stages. First, we selected the most appropriate copula family over a range of possibilities. And then Frank copula turned out to be the best one. And then afterwards, we fitted our model using several values for lambda. Now, as you may remember, in the homoscedastic case, this lambda was fixed. And in theory, it should actually not matter which value of lambda you choose. But we noted that in practice, in the simulations, this lambda does actually impact performance quite a bit. So it would be better to just try out several values and then use AIC to select the best model. And the best model in this case turned out to be a Frank model with an additional restriction, that the correlation be positive, because of course we have this positive dependence between the survival and the censoring time in our liver transplant application. And then you can show using the likelihood ratio test that the selected model is indeed significantly different from the independent. Now, on the level of parameter estimates, what does this look like? So first of all, it's Kendall's tau, so for the association is well, pretty positive. So this is in line with a positive dependence. And on the other hand, the estimate for the regression coefficient beta 1, which is corresponding to the Euclid score, is negative, both in the selected and in the independent model. And this, of course, makes sense because people with a higher Euclid score are more ill, so you would expect them to have a lower survival time. But you can see that there is a discrepancy between the estimate in the dependent case and independent case. This is on the level of parameters, but then it's more easy to interpret this on the level of the quantiles. Now don't look at all the numbers here, but just for instance, for someone with a Euclid score of 55, which is, if I remember correctly, about the mean of the Euclid distribution, we will just have a look at some quantiles. So for instance, on the 30% quantile, what you can see is that the estimated log number of days, of living days left is about 4.7, whereas in the independent model, it is 5.7. So there is a difference of 1 on the log scale, which means that both estimates will differ by a factor, the exponential of 1, in terms of the number of days left. So, and also in other cases, you can see that the independence model will consistently overestimate the remaining survival time of patients on this list. So I hope that with this example, I have convinced you that it's indeed important to take this dependence into account. And it can be interesting to do so using this quantile regression approach that we just proposed. And with this, I will conclude my talk. In case you would be interested in more details, extra simulations, and so on, I invite you to have a look at our preprint that is available on arXiv, or you can always reach out to me by email. And I would be happy to take any questions now as well. Thank you.
Okay, thank you very much, Mirte. I think we still have 4 minutes for questions on either talk. So if anyone has a question, I guess he or she can put it in the chat. If not, then I think we can stop here so that the next session can be prepared to start on time. So I thank everyone for being present. And as Mirte said, if you have any questions, feel free to reach out either to me or to Mirte. So thank you very much and bye-bye.